Welcome to Keentel Engineering. Data centers are not passive loads. This is a technical briefing on EMT modeling for grid stability and AI loads, for data center developers, grid operators, and power engineers. AI facilities behave like inverter-based generation resources. The grid must be modeled accordingly. Let's get into it. EMT, electromagnetic transient modeling, is the highest fidelity simulation method in power systems. What it resolves: microsecond to millisecond transients that are completely invisible to phasor domain models. What it captures: switching behavior of power electronics, control dynamics, and sub-synchronous interactions. The difference from RMS gives you average behavior. EMT gives you full waveform detail. When it's required, loads above 100 megawatts, weak grid interconnections, high inverter penetration, and any situation where oscillation risk is present. If power electronics dominate, EMT is required. 6 data center design archetypes, each with a different EMT profile. 1. Simple, no UPS. Basic power factor correction, common in crypto mining. 2. Centralized UPS, large 3-phase UPS, the most common configuration and the most EMT dominant. 3. Distributed UPS, rack-level batteries, emerging in AI facilities. 4. MVDC distribution, a full DC grid behind the meter, advanced deployments. 5. Medium voltage solid-state transformer, power electronics-based transformation, R&D, and future grid applications. 6. Hybrid BESS plus UPS, battery storage combined with supercapacitors, grid forming capable. Each archetype has a different interaction profile with the transmission system. Know which one you're building. Today's AI server racks draw 100 kilowatts per rack. Near-term trajectory, 1 megawatt per rack. Cooling accounts for 10 to 40% of total load, and the load type is highly dynamic. AI training racks no longer resemble traditional server rooms. They behave like inverter-based generation, ramping hard, cycling on training batches, creating grid-visible oscillations that conventional models don't see. The grid must be modeled accordingly. 3 study areas are critical for any large AI load interconnection. First, oscillatory interactions, the most critical. Sub-synchronous control interaction, sub-synchronous resonance, and forced oscillations from AI training cycles. AI loads excite the 5 to 60 Hz band. That range can damage turbine shafts in nearby generators. Second, voltage and frequency regulation. Required when new inverter technologies are deployed, ride-through performance is uncertain, or the interconnection point is on a weak grid. Grid forming versus grid following control strategy matters significantly here. Third, power quality. Harmonic distortion from switching converters, flicker from rapid AI load changes, and OEM control dynamics that are unique to each vendor. Traditional power quality methods are insufficient. AI training creates grid-visible oscillations on every single batch, and the pattern is consistent. Phase 1, synchronization. All GPUs coordinate before compute begins. Load is minimal, brief, and predictable. Phase 2, forward propagation. Peak GPU utilization, maximum power draw, sharp ramp up, then sustained. Phase 3, reconfiguration. Weight redistribution across nodes. Load becomes oscillating and unpredictable. Phase 4, backpropagation, gradient computation, the hardest compute phase. Often exceeds the forward pass in peak draw. This 4-phase cycle repeats continuously during training. Each cycle is a grid event. SSCI, sub-synchronous control interaction, is the risk EMT was built to find. What causes it? Interaction between converter controls and grid impedance, power electronics near series capacitors on transmission lines, and AI data centers behaving like inverter-based resources. High converter penetration amplifies the risk. The danger zone: oscillations in the 5 to 60 Hz sub-synchronous band. Invisible to conventional phasor simulations, can excite turbine shaft resonance in nearby generators. EMT is the only model that reliably detects it. On compliance, NERC is developing large load modeling guidelines. PRC, MOD, and TPL compliance are all implicated. IEEE 2800 alignment is required for IBR-like loads. An EMT study is required before interconnection approval. 3 technologies address the grid impact of AI data center loads. eStatCom for oscillation damping. Sub-cycle response time greater than 95% oscillation reduction, best applied for SSCI, SSR, and flicker. That 95% figure is the headline. When SSCI is confirmed, eStatCom is the mitigation. BESS for load smoothing and ride-through. Minutes to hours of cycle duration smooths AI training spikes and adds frequency response capability on top. and supercapacitors for fast transient buffering, millisecond response, best for short bursts and inrush events. Energy capacity is the limitation. Each technology targets a different timescale. The right solution depends on which study area is driving the requirement. UPS systems dominate data center grid interaction, and they're the source of one of the most common EMT study findings. Real project, a multi-terminal differential protection problem. Conventional electromechanical relays were causing frequent false tripping, disrupting operations, and accumulating downtime costs. Solution deployed, SEL487E with multi-terminal differential protection. Key feature, dynamic inrush restraint that prevents relay misoperation during normal switching events. Result, 90% reduction in false trips. Financial impact, over $250,000 in avoided downtime costs. EMT role, verified relay settings under all fault and inrush scenarios before commissioning. This is exactly what EMT modeling is for, finding the failure mode before it costs you. Model it before it matters. Keentel Engineering covers the full EMT stack, PSCAD, RTDS, and EMTDC full system models with OEM-specific control integration. Interconnection studies covering SSCI, SSR, voltage and frequency stability, and weak grid analysis. NERC and compliance work across PRC, MOD, and TPL, including large load interconnection and IEEE 2800 alignment. Power quality, harmonic modeling, filter design, and flicker studies from AI load cycles. AI data center consulting, load profile modeling, grid impact mitigation, and storage optimization. And substation and electrical design covering HV/MV substation, protection and control, SCADA, and automation. Reach out at keentelengineering.com or contact@keentelengineering.com.